This is the first one of the Control Systems course videos. In this video, we are going to have a brief introduction to control engineering and its applications, review its history, and give some basic definitions. There are many examples of control engineering all around us. One of the important application areas is the machine tools. In this video, for example, you see a cutting device which cuts a face out of a plexiglass block. Note that the cutting tool is stationary and the table holding the material to be cut is moving in 3 dimensions. The problem here is of course to drive the motors that move the table holding the plexiglass in such a way that the desired shape is cut from this block. Alternatively, the cutting tool besides the table may also be moving. In this case, the motion of the cutting tool must be coordinated with the table. Control engineering can also find applications in nuclear or chemical plants, where you have to control quantities like temperature, humidity, flow rate, or concentration. In the picture, you can see a chemical reaction tank with its control panel and a cooling device to provide the correct temperature for the chemical reaction under control. In this video clip, we have 2 robot manipulators imitating a boxing match. Each robot has a 2-link arm and the links can rotate in different directions. Also, the end effector, namely the boxing glove, can move up and down and around its own axis. So you have many degrees of freedom in moving the boxing gloves. The basic problem here is to determine the motor currents driving the links so that the links are placed at correct angles so as to implement the boxing scenario. Because of the excess degrees of freedom, an end effector position does not directly translate into a unique set of link angles. This problem is known as the inverse kinematics problem of a robot arm, and in determining the angles of your motors, you have to choose for the best of the possibly infinite many solutions. Control of aircrafts and space vehicles are in fact among the important research topics in control engineering. This video clip shows you the test flight of an X-29 aircraft. In an automatic flight mode, the autopilot should manipulate the control surfaces on the wings and the rudder to control the velocity and acceleration of the aircraft in 3 dimensions. So it's a multi-input, multi-output problem. Multi-output because velocity and acceleration in 3 dimensions means that you have 6 different variables to control. It's also a multi-input problem since there are many control surfaces which can be driven independently of each other. Biomedical and biological systems can also benefit from control engineering. In this picture, we have a drug infusion mechanism. Different medical variables such as blood pressure, insulin level can be measured from the patient, and the infusion rate of the drug can be manipulated accordingly. Even in analyzing economical processes, you can use control engineering concepts. Nevertheless, in economics, building reliable models is quite difficult since psychological effects are also in play. Let us have a brief look at the history of control engineering. In the 20th century, we can distinguish between 2 different periods. The first one, which is around 1940s and 50s, I would call as the classical control era. The basic problems of control are tackled in this period. The distinguishing features of this period are the following. Most of the problems investigated in this period are single input, single output problems. In other words, the systems under consideration are assumed to have one input and one output to be controlled. Also, in most cases, frequency domain tools are used. By these frequency domain tools, we mean, for example, transfer function, Bode plots, root locus. These phrases may be strange to you now, but throughout the course, you are going to learn these frequency domain tools. On the other hand, the main concern in this period was stability. That is, the inputs to the system should ensure that the outputs does not grow unboundedly. Stability is another issue that will be among the topics of the coming videos in this course. With the start of the 60s, new achievements in mathematics, especially in optimization theory, were reached. Also by then, computers were available by which you can solve problems that cannot be solved analytically using numerical methods. All these made the analysis of multi-input, multi-output systems possible. So, for example, research on aircraft and space vehicle control boosted during this period. With the availability of numerical and computational methods, the use of time domain tools has also increased. This in turn led to the popularity of the state space approach in modeling dynamical systems. Besides the stability, the performance of control systems were also important during this period. That is, you seek after not only stability, but also optimality, adaptability, and robustness. Optimality, for example, you would like to reach your target in minimum time or by spending minimum fuel. Adaptability, for example, you would like the automatic pilot in your aircraft adapt to different flight conditions at different altitudes. Robustness, for example, you would like to use the same controller in different environmental conditions without losing much from its performance. What we will do in this course will be related more to classical control. That is, we will deal with single input, single output systems. We will explore frequency domain tools like transfer functions, Bode plots, root locus, and we will deal a lot with stability. Occasionally, we will also deal with multi-input, multi-output systems and use state space approach. Let us review some terminology which we are going to use in the sequel. We shall call the quantity or condition that is measured and controlled in a system as controlled variables. A more commonly used and shorter term for this is output. On the other hand, the quantity or condition varied by the controller to affect the controlled variable is called as manipulated variable. Another term for manipulated variable is control input or simply input. A plant is a physical object to be controlled. As in the common use of this word, it can be, for example, a nuclear or chemical plant, or it can be any system under control like an aircraft, a space vehicle, or a robot manipulator. In some cases, we may prefer to use the word process, since process covers a wider range of systems like ecological, biological, or economical processes. System, on the other hand, is a more general term referring to any collection of components that act to perform a certain objective. In many cases, systems are exposed to signals or conditions that has adverse effects on the output. Such signals or conditions are called disturbances. Impurities in a chemical process or side winds for an aircraft can be considered as disturbances, for example. One of the most important terms which we will use frequently in this course is feedback. Feedback control is defined as the operation that aims to reduce the difference between the output and some reference input using this difference. Let me emphasize once more two important phrases in this definition. So, we would like to reduce the difference between the output and some auxiliary input, and we would like to do this using this difference. That means we will need to measure and monitor the output of the system. Feedback control is also known as closed-loop control. Let us now differentiate closed-loop and open-loop strategies. For example, basic blocks of a system to control the temperature in a room can be shown as in this figure. The plant in this example is considered as the room, or rather the heat dynamics of the room. The temperature in the room can be measured by a temperature sensor, a device commercially known as thermocouple. Most of the components that are used in this feedback path going from the output to the input side are devices that convert one physical quantity to another, known as transducers. The controller compares the desired temperature set by the user to the measured temperature in the room and commands the heater or air conditioner. The air blown by the heater or air conditioner is expected to drive the temperature in the room to the desired value through the dynamics of the room. Note that the aim is to equate the room temperature to the desired one, and this is achieved by monitoring the difference between the desired temperature and the actual temperature. What about the open-loop control? Well, one of the well-known examples of the open-loop control is the operation of a washing machine. The aim of a washing machine is to clean the clothes. Nevertheless, during the operation, the cleanness of the clothes are not measured. Instead, the washing machine runs a preset sequence of operations, one after the other, without really caring whether the desired cleanness level has been reached or not. To conclude this part, we are going to compare feedback control and open-loop control from different points of view. The sensitivity of a system under closed-loop control to disturbances is less than that of an open-loop controlled system. Since the output is measured during the operation, closed-loop control can take care of adverse effects of the disturbances better. On the other hand, stability is a problem to be considered in the closed-loop control case. When we say a problem to be considered, we mean it in two ways. First, if a system is unstable, you can use closed-loop control to stabilize the system. That is, you can solve the stability problem of the system. Secondly, when you are using closed-loop control, and if the system is stable, you have to take care not to drive the system to instability. Under open-loop control, stability is not considered as a problem, since open-loop control cannot affect the stability of a dynamic system. Also, the closed-loop control systems would require more components, as one would need extra devices to implement the feedback path. That means they are expected to be more expensive and power-consuming as compared to open-loop controls. However, closed-loop control systems would hardly require calibrations. As we shall see in the forthcoming videos, one of the major advantages of feedback operation is to make the system insensitive to variations in the plant dynamics. Open-loop control, on the other side, may require frequent calibrations of the controller.